Welcome to NDT Decoded, the podcast where non-destructive testing stops being a textbook chapter and starts making real engineering sense. I am your host, and joining me is Professor Evanivaldo Correa, a leading voice in quality inspection, NDT methodology, and industrial engineering education. Evanivaldo, thank you for being here with us today.
Thank you for having me. It is a pleasure to walk through this material with students and professionals who want to understand why visual inspection remains the cornerstone of structural safety.
Today we are doing something a little different. We are covering the complete foundation of visual testing. We will walk through its history, the optics and physiology behind it, the equipment inspectors actually use, the precise terminology that keeps reports unambiguous, how procedures are structured in real plants, and finally, how these methods play out in automotive manufacturing, petrochemical complexes, and aerospace engineering. If you are an engineering student, this episode is designed to be your audio textbook. Take notes, pause when you need to, and let us decode NDT together. Let us start at the beginning. Evanivaldo, when students hear visual testing, they often assume it is just looking at a part. Why is that assumption so misleading?
It is misleading because it ignores the standardization. Visual testing, or VT, is the oldest and most widely utilized non-destructive examination method in modern industry. At its core, it involves the systematic examination of a component, structure, or joint to identify surface discontinuities, geometric deviations, corrosion, weld defects, or misalignments without compromising the integrity of the material under evaluation. While it may appear intuitive, standardized VT is grounded in optical, physiological, and procedural principles that establish it as a reproducible technical discipline.
So it has always been around. But when did it become an actual engineering discipline?
Its origins trace back to early craftsmanship and metallurgy. Blacksmiths and boilermakers assessed cracks, porosity, or deformations with the naked eye. However, VT became formalized as a quality control method during the Industrial Revolution and the subsequent expansion of aviation and shipbuilding. By the mid-20th century, organizations such as the American Society for Non-Destructive Testing and the American Welding Society began standardizing inspection distances, illumination levels, required visual acuity, and acceptance criteria. Today, VT is officially recognized as the first step in any NDT workflow. Other methods like ultrasonic testing, radiography, or magnetic particle testing are rarely applied without a preliminary visual evaluation to rule out obvious flaws or to identify critical zones for further investigation.
That makes sense as a filter. But what actually governs whether an inspector sees a flaw or misses it? Is it just eyesight?
Not at all. The effectiveness of visual inspection depends not only on the inspector visual acuity, but on the controlled interaction between light, surface characteristics, and human perception. Three technical factors govern this process. First, illumination. The standard ISO 17637 specifies a minimum of 350 lux for general inspections and up to 1000 lux for critical details or high-demand welds. Lighting must be diffused to avoid specular reflections that could mask cracks or porosity. The angle of incidence typically ranges between 30 and 60 degrees relative to the surface to maximize discontinuity contrast.
And the surface itself changes how we see it.
Absolutely. Surface finish, base color, humidity, dust, vibration, and temperature all directly affect reflectivity and detection capability. Fluctuating lighting or surfaces contaminated with oil or grease can reduce effective sensitivity by more than 40%. Then there is the human factor. Visual perception and acuity require corrected vision, typically 20/20 or equivalent, plus color discrimination and sustained attention. Visual fatigue fatigue is a documented limiting factor. Technical procedures mandate periodic breaks and task rotation during prolonged inspections. You cannot engineer around biology. You must design for it.
So when we actually go out to inspect, how do we decide whether to look directly or use tools?
We split the approach into two modalities. The direct method means unaided observation within strict geometric constraints. Standards typically require a maximum viewing distance of 600 millimeters and a minimum viewing angle of 30 degrees. It is used for immediately accessible inspections, basic dimensional control, and verification of surface cleanliness or corrosion. The indirect method is employed when geometry, safety constraints, or component size prevent direct visual access. This approach relies on optical and electronic devices that magnify or transmit the image. Equipment selection is never arbitrary. It is determined by component geometry, accessibility, required resolution, and the need for documentary records.
So before we even talk about defects or procedures, we have established that VT is a science of light, human physiology, and controlled observation. It is the mandatory starting point for every other NDT method. Let us move into the hardware and the vocabulary. Evanivaldo, what terms should students know before they ever pick up a borescope or a magnifier?
Visual testing relies on standardized terminology to ensure consistent communication between inspectors, engineers, and quality personnel. Key terms include optical axis, field of view, resolution, depth of field, and contrast sensitivity. The optical axis refers to the straight line along which light travels through an inspection device. Field of view defines the observable area at a given working distance, while resolution indicates the smallest detail that can be distinguished. Depth of field determines the range over which the image remains acceptably sharp. Contrast sensitivity measures the ability to detect a flaw against its background. In industrial practice, these parameters are quantified to match inspection requirements with equipment capabilities. Another critical concept is the acceptance criterion, which establishes the maximum allowable size or severity of a discontinuity based on applicable codes.
And how does human vision actually interact with these parameters?
Human vision operates through the interaction of light with photoreceptor cells in the retina. Cones provide color discrimination and detail recognition under adequate illumination, while rods enable detection in low light conditions but lack color sensitivity. Effective visual inspection requires a minimum illuminance of 350 lux on the inspection surface, with critical applications demanding 1000 lux or higher. Illumination must be uniform and diffused to prevent glare, which can obscure surface anomalies. The angle of incidence significantly affects defect visibility. Light striking a surface at a shallow angle, known as grazing incidence, casts shadows that reveal cracks, scratches, or uneven weld profiles. Material attributes such as reflectivity, surface roughness, oxidation state, and color directly influence how light interacts with the component.
What about the tools themselves? Students see mirrors, borescopes, endoscopes. How do we choose?
Inspection mirrors are constructed with first surface aluminum or dielectric coatings to minimize double imaging. They are available in flat, concave, or articulated configurations, with diameters ranging from 25 to 150 millimeters. Magnifiers utilize achromatic lenses to reduce chromatic aberration, with standard magnifications between 2 times and 10 times. For precision work, calibrated reticle magnifiers enable dimensional measurement directly in the optical path. Borescopes consist of rigid relay lens systems housed in stainless steel tubes. They provide high-resolution, undistorted images with working lengths from 100 millimeters to several meters. Articulating models feature distal tip deflection up to 120 degrees, enabling navigation through complex internal passages. Fiber optic scopes transmit images through coherent glass fiber bundles. They offer flexibility and durability, but exhibit lower resolution and a characteristic pixelated texture due to fiber spacing. Modern digital endoscopes replace fiber bundles with miniature CMOS sensors at the distal tip, delivering high-definition imaging, adjustable LED illumination, and onboard measurement software. Closed-circuit television systems integrate pan-tilt zoom cameras with remote monitoring capabilities, primarily used for large-scale or hazardous inspections. Light sources must match inspection requirements. White LED arrays provide uniform daylight-matched illumination. UVA lamps at 365 nanometers activate fluorescent penetrance. Polarized filters reduce reflective glare from metallic surfaces.
I imagine it is easy to over-rely on magnification.
Yes, it is a common error to assume higher magnification always improves detection. In reality, excessive magnification reduces field of view and depth of field, making it harder to locate anomalies. Conversely, insufficient lighting or improper angle selection can render visible defects undetectable. Calibration and maintenance are non-negotiable. Optical surfaces must remain free of scratches and contamination. Illumination intensity should be verified periodically with calibrated lux meters. Digital systems require sensor validation and software version control to maintain measurement accuracy. In modern engineering workflows, visual inspection equipment is integrated into standardized inspection plans rather than used as isolated tools. Engineers specify required resolution, minimum illumination, and acceptable distortion levels in procedure documents. When properly selected, maintained, and applied within documented procedures, visual inspection equipment transforms subjective observation into quantifiable, repeatable engineering data.
Let us talk about the language of materials. This is where students often get tripped up. How do we classify what we are looking at?
In visual testing, precise material identification is the foundation for accurate defect assessment. Base material refers to the primary substance from which a component is manufactured, prior to any joining, coating, or thermal treatment. Metallic materials include ferrous alloys such as carbon steel, stainless steel, and cast iron, as well as non-ferrous metals like aluminum, copper, titanium, and their alloys. These materials typically exhibit characteristic visual indicators: metallic luster, grain structure visibility after etching, oxidation patterns, and specific corrosion morphologies such as uniform attack, pitting, or stress corrosion cracking. Mineral-based materials, including ceramics, glasses, and refractory compounds, display distinct optical properties such as translucency, crystalline fracture patterns, or thermal shock damage. Organic-based materials encompass polymers, elastomers, adhesives, and composite matrices. These materials require different visual evaluation criteria, including color change due to UV exposure, surface crazing, delamination, blistering from chemical attack, or fiber exposure in reinforced composites. Correct material classification directly influences the selection of illumination type, magnification level, and acceptance criteria during inspection.
And when we look at welds, what terminology matters most?
Welded joints represent critical inspection zones where visual testing is most frequently applied. A weld bead is the visible deposit of filler metal fused to the base material during the welding process. Key geometric features include weld face, toe, root, reinforcement, and heat-affected zone. Common surface discontinuities detectable by VT include undercut, which is a groove melted into the base metal adjacent to the weld toe; porosity, which are gas pockets visible as small surface openings; slag inclusions, which are non-metallic residues trapped at the surface; lack of fusion, which appears as incomplete bonding or linear separations; and crater cracks, which are star-shaped fractures at weld termination points. Acceptance of these features depends on applicable codes such as AWSD 1.1 or ASME Section 9, which define maximum allowable dimensions based on service conditions. Terminology: precision is essential. A discontinuity becomes a defect only when it exceeds code-specified limits.
That distinction keeps coming up. Discontinuity versus defect. Why is it so critical?
A fundamental concept in non-destructive evaluation is the distinction between discontinuity and defect. A discontinuity is any interruption in the normal physical structure of a material, including cracks, pores, inclusions, seams, or geometric deviations. Discontinuities are inherent to manufacturing and service. Their presence alone does not imply component rejection. A defect is a discontinuity that exceeds the acceptance criteria established by the applicable design code, specification, or engineering judgment. For example, a 0.5 mm surface pore in a non-critical bracket may be acceptable, while the exact same pore in a pressure boundary component could constitute a defect. This distinction requires inspectors to reference documented criteria rather than rely on subjective assessment. Visual testing procedures must explicitly state the governing standard, the inspection class, and the quantitative limits for each discontinuity type. Training programs emphasize this differentiation to prevent both unnecessary rework and unsafe component release.
So the vocabulary is not just for reports. It is the decision framework.
Exactly. Definitions gain operational value when embedded into structured inspection workflows. Procedure documents begin by specifying the material type, component geometry, and service environment to establish the relevant terminology framework. Inspection objectives then reference these definitions to target specific discontinuity types. Inspection points are selected based on material behavior and historical failure data. Sampling plans define how many components or areas require examination using statistical terminology aligned with standards like ISO 28591. Documented procedures incorporate visual references, photographs, diagrams, or physical samples to calibrate inspector interpretation of terms such as acceptable reinforcement or critical porosity. When definitions are consistently applied across planning, execution, and reporting phases, visual inspection achieves the repeatability and traceability required for engineering decision-making.
Let us move from terminology to execution. How do we actually write and run a visual inspection procedure?
Every effective visual inspection begins with clearly defined objectives that align with engineering requirements and quality standards. Inspection objectives specify what discontinuities or conditions must be detected, such as surface cracks exceeding 0.5 millimeters, corrosion coverage greater than 10%, weld profile deviations beyond code limits, or misalignment of assembled components. These objectives are derived from design specifications, service environment analysis, regulatory requirements, and historical failure data. Planning also includes defining the inspection scope, whether the evaluation covers 100% of components, a statistically valid sample, or only critical zones identified through risk assessment. Engineers must document the applicable codes such as ASM, EBP, VC Section 5, AWSD 1.1, or ISO 17637 to ensure acceptance criteria are unambiguous. A well-structured plan assigns responsibilities, specifies required equipment calibration status, and establishes environmental controls such as minimum illumination and acceptable temperature ranges. Without this foundation, visual inspection risks becoming inconsistent, subjective, or non-compliant with quality assurance protocols.
And how do we know where to look? Not every square millimeter gets the same attention.
Identifying critical inspection points requires systematic analysis of component geometry, load paths, and surface exposure. High-stress zones such as weld toes, section transitions, bolt holes, and support interfaces are prioritized because they concentrate mechanical loads and are prone to fatigue initiation. Engineers obtain and review technical drawings, isometrics, weld maps, and assembly diagrams to understand nominal dimensions, tolerances, surface finish requirements, and material specifications. Drawings provide the reference geometry against which visual observations are compared. For welded structures, Weld symbols and joint details indicate expected profiles and acceptable reinforcement limits. For machined components, datum features and geometric dimensioning tolerances guide alignment verification. Inspectors must verify that drawings are current revisions and that any engineering change orders have been incorporated. When digital models are available, three-dimensional visualization tools can highlight hidden features or complex geometries that require indirect inspection methods. This drawing-based preparation transforms visual inspection from a general survey into a targeted engineering evaluation.
What about production lines? You cannot inspect every single part manually at high speed.
When inspecting production lots or large component populations, statistical sampling ensures efficient resource allocation while maintaining quality confidence. Sampling plans follow internationally recognized standards such as ISO 28591 or ANS-IAS-QZ 1.4. which defines sample sizes and acceptance numbers based on lot size and inspection level. General inspection, Level 2, is commonly applied for routine visual checks, while tightened or reduced levels adjust scrutiny based on process stability. Attribute sampling classifies each unit as conforming or non-conforming against predefined visual criteria, such as presence of surface cracks or dimensional out-of-tolerance conditions. Variable sampling, though less common in pure visual testing, may incorporate measured parameters like weld reinforcement height or corrosion depth when supported by calibrated optical tools. Inspectors must document the sampling rationale, selection method, and handling of non-conforming units. Batch evaluation protocols also specify re-inspection procedures for rejected lots and escalation paths when defect trends emerge. Proper sampling balances inspection effort with risk management, ensuring that visual testing supports both quality control and production efficiency.
And how does all of this tie into broader quality systems?
Visual inspection procedures gain strategic value when integrated into broader quality management systems such as ISO 9001 or IATF 16949. Inspection records feed into non-conformance management systems, enabling root cause analysis, corrective action tracking, and process improvement initiatives. Trend analysis of visual findings can reveal emerging issues such as tool wear, material batch variability, or environmental degradation before they escalate into field failures. Digital inspection systems enhance this integration by linking images, measurements, and inspector comments directly to component serial numbers and enterprise resource planning databases. Training programs reinforce procedure adherence through competency assessments, blind sample testing, and periodic requalification. Management review cycles evaluate inspection effectiveness using metrics such as defect escape rate, rework cost, and customer complaint frequency. When visual inspection is positioned not as an isolated checkpoint, but as a data-generating node within a learning organization, it contributes directly to product reliability, operational excellence, and customer trust.
We have covered the theory, the tools, the definitions, and the procedures. Now, let us ground this in reality. Where do we actually see this playing out across industries?
In the automotive sector, visual testing is embedded throughout the production chain, from raw material receiving to final assembly validation. Body-in-white inspections focus on weld quality in stamped steel panels, where inspectors verify spot weld count, nugget formation, and absence of surface cracks using direct VT with calibrated magnifiers and grazing incidence lighting. Robotic vision systems complement human inspectors by performing 100% screening of weld seams at line speed, flagging deviations for manual review. Powertrain components, such as engine blocks and transmission housings, undergo visual examination for casting defects, including cold shots, porosity, and sand inclusions. Borescopes are routinely deployed to inspect internal oil galleries and coolant passages without destructive sectioning. In electric vehicle battery assembly, visual inspection verifies cell alignment, busbar weld integrity, and sealant continuity with UV-assisted lighting used to detect fluorescent tracer leaks. Industry standards such as IATF 16949 and AIAG CQI9 define visual inspection requirements, including inspector qualification, lighting verification, and defect classification matrices. The high-volume nature of automotive production demands that visual procedures balance detection sensitivity with cycle time, often employing statistical process control charts to monitor visual defect trends and trigger preventive maintenance before quality escapes occur.
And what about harsh environments, like petrochemical plants?
Visual inspection in petrochemical facilities addresses components exposed to extreme temperatures, corrosive media, and cyclic loading. External corrosion monitoring on pressure vessels, piping, and storage tanks relies on systematic visual surveys documented through digital photography and corrosion mapping software. Inspectors apply ISO 17637 lighting requirements while accounting for field constraints such as confined space entry, elevated work platforms, and hazardous area classifications. Indirect methods dominate internal inspections. Fiber optic borescopes examine tube bundles in heat exchangers, while remote video crawlers assess furnace tubes and reactor internals during turnaround outages. Specialized techniques include wet fluorescent magnetic particle inspection preceded by visual cleaning verification and dye-penetrant examination, where surface preparation is confirmed visually before chemical application. API 510, API 570, and API 653 provide sector-specific visual inspection criteria for pressure vessels, piping, and tanks respectively, defining acceptance limits for corrosion thinning, crack indications, and weld degradation. Environmental factors such as humidity, salt spray, and hydrocarbon vapors require inspectors to select corrosion-resistant equipment and implement strict contamination control procedures. Risk-based inspection frameworks prioritize visual examination frequency based on consequence of failure, ensuring resources focus on high-risk assets while maintaining regulatory compliance.
And aerospace? That is often the highest tier of scrutiny.
Aerospace visual inspection represents the highest tier of procedural rigor, where defect detection thresholds reach sub-millimeter scales and documentation requirements support airworthiness certification. Composite airframe structures undergo detailed visual examination for delamination, impact damage, and fiber breakage using controlled lighting angles and polarized filters to enhance contrast. Metallic components such as turbine blades, landing gear, and fastener holes are inspected for fatigue cracks, fretting corrosion, and foreign object damage using high magnification optics and surface replication techniques. NADCAP 7114 defines audit criteria for visual inspection processes in aerospace suppliers, mandating equipment calibration records, inspector certification to NAS 410 or EN 479, and traceable defect reporting. Digital endoscopes with measurement software enable dimensional verification of internal features in assembled engines without disassembly, reducing maintenance time while preserving component integrity. Foreign object debris prevention programs integrate visual inspection at multiple assembly stages, with cleanroom protocols and white glove audits, ensuring no contaminants remain in flight-critical systems. The consequence of visual inspection failure in aerospace drives redundant verification steps. Critical features often require independent inspection by two qualified personnel, with disagreement resolution through engineering review boards. This layered approach ensures that visual testing, despite its apparent simplicity, meets the zero-defect expectations of flight safety.
So across these three sectors, what remains constant?
Although automotive, petrochemical, and aerospace applications differ in scale, environment, and regulatory framework, they share foundational visual testing principles. All three sectors require defined inspection objectives linked to component function and failure modes, calibrated equipment matched to required resolution and accessibility, documented procedures aligned with applicable codes, and qualified personnel whose visual acuity and decision criteria are periodically verified. Adaptive strategies emerge from sector-specific constraints. Automotive prioritizes speed and statistical confidence for high-volume production. Petrochemical emphasizes environmental resilience and risk-based prioritization for asset integrity. Aerospace demands traceability, redundancy, and sub-millimeter detection for flight-critical reliability. Engineers designing visual inspection programs must therefore balance universal best practices with context-specific adaptations. Emerging technologies such as artificial intelligence-assisted image analysis, augmented reality guidance for inspectors, and cloud-based defect databases are beginning to enhance traditional visual methods across all sectors. However, these tools augment rather than replace the core engineering judgment that distinguishes professional visual testing from casual observation.
Where is this going next? What should students prepare for?
The enduring value of visual testing lies not in its technological sophistication, but in its capacity to integrate human pattern recognition with structured engineering criteria. As automation and digitalization advance, the inspector role evolves from manual detection to data interpretation, procedure optimization, and cross-functional collaboration. Final year engineering students entering industry must therefore master both the technical fundamentals of visual testing and the systems thinking required to embed inspection within broader quality, reliability, and safety frameworks. Continuous learning remains essential. Standards evolve, new materials introduce novel failure modes, and digital tools create new capabilities and validation challenges. By grounding visual inspection practice in verifiable principles, documented procedures, and sector-appropriate adaptation, engineers ensure that this foundational NDT method continues to protect product integrity, operational safety, and public trust across the global industrial landscape.
Thank you, Ivanivaldo, for walking us through the complete architecture of visual testing. To our engineering students listening, if you take away 3 things from this episode, let them be these. First, visual testing is never just looking. It is a controlled interaction of light, physiology, and procedure. Second, a discontinuity is not a defect until it crosses a documented acceptance limit. Your job is to know that limit before you inspect. Third, equipment, sampling, and reporting are not administrative tasks. They're the engineering backbone that turns observation into traceable data.
I would add one more. Do not skip the fundamentals. Every advanced NDT method, every AI-assisted vision system, every automated crawler builds on the optical and procedural discipline we discussed today. Master the baseline, and everything else becomes an extension of your judgment.
In our upcoming episodes, we will dive into ultrasonic wave propagation, magnetic particle physics, and radiographic interpretation, always linking back to these core visual principles. Keep your standards high, your lighting calibrated, and your observations documented. This has been NDT Decoded. I am your host, alongside Professor Ivanivaldo Correa. Thank you for listening, and we will see you in the next session.